Good afternoon, everyone. We are Team 1, and we are going to present what we have done throughout the project, Transpose, and what we will do further to improve our systems. My name is Tinsel Lee, and let me begin today's presentation. We will give you a brief introduction, including background first. Then we will explain how we actually replicated and improved further the original paper, and we will end our presentation by discussing the limitations and the directions for the future works. It's been a long time since our last presentation, so you may forget what our project is about. Therefore, I briefly introduce what the baseline paper was. We selected the paper Transpose, Real-Time 3D Human Translation and Post-Estimation with 6 inertia sensors as our target, which was presented at SIGGRAPH 2021. It was about capturing the motion with 6 IMUs. An IMU stands for an inertial measurement unit that measures angular weights, specific force, and etc. using accelerometers and gyroscopes. But you may wonder why we should pay attention to motion capture. Actually, motion capture is gaining more and more attention as it can be used in various domains with superior performance. To name a few, game industry and film industry are actively employing motion capture technology for CGI effects. Also, various robotics researchers are also interested in this field. Even some of medical scientists and NLP scientists also have interest in motion capture, as you can see from the given studies. Then, why did authors focus on IMUs? To understand this, you should first know the common approach in this area. There are two different methodologies, optical systems and non-optical systems. As their names indicate, the main difference between them is whether the system incorporates cameras or not. If you use cameras, then you usually need to attach markers everywhere on your body, and you should set dozens of cameras in the room to achieve high accuracy. Then, as you can easily guess, it causes skyrockets as the number of cameras increases. Also, your body movement is constricted by the number of annoying markers. Even worse, if there is any obstacle between the camera and you, then the system cannot correctly capture the motion. We call this phenomenon truncation. All of this limitation can be overcome by employing non-optical system, which using IMUs, and this is why the author focuses on IMUs. Now let's move on to the next part. Here I will continue introducing our project, focusing on how we replicated the paper and what we plan to improve it. For the first step, we collected the datasets and the code base provided by the authors. Fortunately, we could locate the GitHub repository of the authors, so we could get codes and data from there. Though most of codes were fine, the training code was not the case, so we should write our own training code. Also about the datasets, we could not find any IMU-related data there, but only SMPL and AMSS, which are publicly available datasets. So we synthesized IMU dataset from these two datasets using the provided code. And as we wrote the new code for the training model, we should also modify the model slightly. Please note that we pay special attention not to alter its semantics, but only to make it runnable with our new training code. From now on, we call this model baseline, as it's the original model designed by the authors, which we want to improve. Now let's move on to our original plans. First, our main improvement plan was reducing number of sensors. We thought that 6 IMU sensors was still too many. The advantage of IMU sensors is that they are light and small. This means that it's easy to attach directly to our bodies, but it also means that it's already built into and can be built into many smart devices around us. We would be better off getting information from the devices and sensors we already use rather than attach additional sensors to our bodies. Considering smartphones, smartwatches, and wearable devices worn on the head, we decided on the following 4 joints as new leaf joints: left hip, right hip, left wrist, and forehead. However, just setting new leaf joints cannot solve the problem, so we need a working model even with a similar number of joints. Additionally, the computational cost of the existing training code was too high, so we also tried to make it better by simplifying it. Now Jong-hee will continue our presentation.
Done, and now I'll be presenting our contributions. First, I'll clarify what we're doing. We are improving our original paper Transpose by reducing the number of IMU sensors. And the problem that we faced by doing so was that the original model gave unnatural movements and high computational cost. And our solutions were to make a new loss function along with a new model. And now I'll talk about what changes we have made for these three colored sections. First, about IMU sensor reduction. In our project, we leverage two distinct types of IMU data. The first is synthetic IMU data, specifically the AMS dataset utilized for training our model. The second is real IMU data sourced from the DIPI IMU dataset and is employed exclusively for testing. Originally, these datasets were extracted from 6 regions of our body, as illustrated in the left diagrams of both AMS and DIPI IMU figures below. However, we have extracted new data for both AMS and DIPIMU from the left hip, right hip, left wrist, and forehead, as showcased in the corresponding right diagrams. Now let's talk about our new loss function. We focused on reducing the computing cost and further expected it to enhance the jitter error. In detail, we've implemented a significant enhancement by revisiting the trans B2 loss function. Previously, it was both repetitive and overly complex. As a solution, we simplified it by adopting a straightforward mean-squared error loss. In addition, we streamlined the training process to eliminate the time-consuming conversion of a rotation matrix to 6D. Instead, we opted to directly use the rotation matrix itself. This modification not only improves efficiency, but also maintains the integrity of the training process. And for our new model structures, we also aim to reduce the computing cost along with giving better performance. We introduced 4 key modifications to enhance our model. First, we applied a transformer encoder to augment its capabilities. Second, we experimented with different activation functions and layers to explore various architectural configurations. Third, we conducted a fundamental reformation to address core aspects of the model structure. Lastly, we fine-tuned the hyperparameters to optimize overall performance. Leveraging these 4 major adjustments, we iteratively refined the baseline model, resulting in the creation of 10 new models, as detailed in the table on the right. These enhancements signify our commitment to methodical improvement, ensuring that models are not diverse but also finely tuned to achieve superior performance. Here are some details about our key modifications. We have changed the LSTM part to a transformer encoder as so. Modified ReLU used in between L2 and L3 with other activation functions, and also changed L3 and L4 to GRU cells or RNNs. And lastly, what we meant by fundamental reformation was that we forwarded IMU history rather than the RNN hidden states, as shown in this diagram. Having covered our methodology, let's delve into our results. Notably, our implementation of a new loss function and training method has yielded a remarkable reduction in the time required for both pre-processing and training. The processing time has seen a substantial decrease, plummeting from 3,345.31 seconds, equivalent to 55 minutes, to a mere 9.67 seconds. Additionally, the time taken for a single epoch of training has been significantly reduced to 33.29 seconds. Moreover, a closer examination of the live demo reveals an improvement in jitter error, resulting in more natural and refined movements. Turning our attention to models trained with our new loss function and comparing them to those trained with the original loss, we observed a significant and noteworthy improvement. However, we were able to see some trade-offs that accompany these gains, particularly in terms of slight increases in other error metrics. Now, directing our attention back to the same table that represents the results of our new models trained and tested on the original 6 sensor datasets. In this analysis, we observed that models from NYO5 to NYO7 exhibit some reductions in other error metrics, all while maintaining consistently low jitter error. This trend persisted when the models were trained on the new 4 censored IMU datasets. Consequently, we have selected NYO5 to NYO7 as our candidate best models. However, when we looked at the training graph of these models on the new force sensor dataset, we were able to see that NYO5 showed exceptional training loss and convergence speed. This implies that NYO5 requires significantly fewer epochs for sufficient training while maintaining high performance. This efficiency not only contributes to time savings, but also underscores the robustness and adaptability of NYO5 in capturing the underlying patterns within the new force-censored IMU dataset. Consequently, we advocate for the adoption of NYO5 combined with our new loss as our solution for achieving a balance between low computational cost and high performance. This combination has demonstrated a substantial reduction in jitter error, offering a commendable trade-off for other error metrics. Notably, it contributes to lower time costs for training through its fast convergence and minimized redundancy. Lastly, we've evaluated our NIO5 model with a live demo. We've compared it with baseline and new. New has too much jittering happening and also showed a fixation of its right foot. Baseline could improve the jittering, but couldn't fix the right foot's fixation. However, NYO5 gave a good sweet spot of jittering and the fixation of the right foot. Moreover, in this course of the project, we identified a trade-off between translation and jittering. As illustrated in the video, when jittering improves, the motions become more natural, but there is an observable increase in the person's movement across the field. We consider this to be a pivotal point for potential model enhancements and further refinement of loss selection strategies.
And hi, I'm Yuno, and it's our last part discussion. So first, think about our limitation. One of the limitations is that natural motion could not be created for DIP IMU dataset or real IMU sensor data. Motion that from AMS data, which is synthetic data, works well, but when looking at the DIP IMU dataset, the motion did not seem natural. We think the biggest reason is contact probability. Following the method of the paper, we fixed the foot and reconstructed the motion using the concept of contact probability. At that time, as the model is training, a trade-off between translation and jitter occurs. As the translation error gets smaller, the jitter error increases, and as the jitter error gets smaller, the translation error increases. We think a more sophisticated losses is needed. And additionally, we exclude body part where the IMU sensor is far away or unknown, such as finger and foot, so full body tracking was impossible. And finally, let's think about our future work. For our new dataset, parts of the body that do not have IMU sensor are either not predicted at all or are omitted from the loss calculation. However, instead of using this method, we thought that appropriate motion could be created using a diffusion model. These days, many diffusion models are being created in the image field. However, there is not much data about motion yet, and there are not many diffusion models for motion too. Rather than simply applying a diffusion model, a system that can collect data and utilize that data may be needed. And additionally, our ultimate goal in reducing the number of joints was to predict motion using sensor in wearable device such as actual smartwatch or smartphone. And by evaluation, we checked using real sensor is possible, so it could be used with actual wearable device with considering issues such as normalization or calibration or different value for each sensor. And this is the end of our presentation. Thank you for listening, and please feel free to give any comments, question, or feedback. And thank you.